welcome back. We are going to have the next session with the title From Command Line to User-Centric HPC Democratizing Access to Biomedical Research at IEO, European Institute of Oncology. Our speakers are Chiara Bosso, Biomedical Engineer, and Vafaei Rad, Digital Biologist, both of them from the European Institute of Oncology.
So, good morning, everybody. Yes, maybe we are all. I'm Chiara, and I'm here with Ali from the European Institute of Oncology. Now we will share with you the way we improve the accessibility, reproducibility, and heterogeneity in our cluster environment. So, just a few words about that. Our institute was founded in 1994 by Umberto Veronesi. It is a comprehensive cancer center. It can be divided into two parts that are the IEO hospital, in which the clinical activities are performed, and the IEO campus, where we work, in which research and clinical studies are performed. We have an integrated model of care, research, and education, and in our institute, especially in the campus, there are more than 20 research groups. It can be divided into a research community that is managed by the principal investigators and technological unit. Our technological unit, that is the Advanced HPC and Data Engineering, operates, as is written, the computational ecosystem connecting researchers, technology units, and data-intensive biomedical workflows. So, our team is very small but dedicated. We are Chiara. I am a biomedical engineer. Ali, he's a digital biologist, and Gianpaolo, that today had to stay in Milan to work with the other researchers, is a bioinformatician. We work under the strategic overflow of Anna Rosa Farina, that is the IT system manager in IEO, and the CCM, that is the Centro Cardiologico Monzino. We work under different types of tasks, but under the same focus areas that are HPC operations, user support, workflow, reproducibility, data lifecycle, and so on. We deal also with some virtual machines, cloud services, and some other applications that can be used from the campus or the hospital. The challenge that we wanted to deal with is the fact that in our institute there are a lot of people that are not daily working with biocomputational or informatics tasks, because there are a lot of, for example, wet lab researchers, PhDs, and so on. So traditional command line HPC access limits the adoption among non-specialist users. So we decided to transform our old system, HPC cluster, to a new HPC cluster, also with the help of Do It Now systems, and the impact, as we will see, was very, very good. This migration was adopted in October 2025. In this slide, you can find some differences about the old system and the new one. There are some technical information, and in particular, the resilience, the scalability, the reproducibility were very good, and also with the introduction of the GPU acceleration, we improved the analysis that sometimes, for example, took days. Now they took hours. So our system was very good. So the thesis was that by starting from an old system based on CLI barrier and PBS legacy, okay, I'm doing two switches, so sometimes we obtained a new system based on SLURM as a workload manager and open on demand for accessing by web portal in order to obtain a wider adoption between the biomedical users. Some numbers that you can find are about the users that are daily supported and that are daily using our HPC cluster, that are about 200. More than 50 new users reached the cluster after the migration. Some of them are not bioinformaticians, so they are wet lab researchers and so on. 90% of them, of the community, access via open on demand. So it was very useful in order to adopt our HPC cluster also to the other people. Our platform can be divided into 5 parts that are as equal in importance, that are workload management, performed by SLURM, user interface by Open On Demand, software ecosystem by Lmod modules, EasyBuild installs that contribute to reproducible software management and environments, data layer that, as we will see, is very important in our institute because of the sensitivity of the data, and also operations like monitoring with Grafana. So this slide and the next one will be dedicated to the access model. So the first login needs to be performed by SSH access in order to create the environment and the home directory by the user. Then the next other accesses can be performed via Open On Demand, so via browser. Then you land on the login nodes. We have 2 login nodes, and then you can access to the computational resources that can be managed by SLURM. In this slide, you can have a look to the schema of some information that I have told to you. Then there is also another schema about the class of nodes that were adopted that we will see in the next slide, and also a kind of other schema about the storage partitions and management. What about the nodes? So here in this slide, you can find the node inventory. So we have different classes of nodes because especially in our institute, biomedical data and workflows are very heterogeneous. So we needed a cluster that was heterogeneous in partitions, in storage, in node inventory, and also in the other type of data that are managed. So we can find the login nodes, then we have 8 compute nodes, a FET node that can be used, for example, for heavy workloads, and then 2 different GPU classes of nodes that are the GPU 01, in which there are 8 H200 NVIDIA GPUs, and then the visualization ones that are 2 visualization nodes, L40s. What about the SLURM partitions? We have 4 partitions. Recently, we have adopted another one that is the bioinfo genomic partition that can be used, for example, for genomic pipelines to be run with another type of priority respect to the others. The short partition is the default one. They differ in time limit, nodes, features, and so on. And as you know, SLURM follows a fair sharing policy, so to each job, to each user is given a different type of priority that depends on the tasks that the users needed to do. And so a score is assigned to the user, and it makes our cluster very democratic in use. Briefly, in this slide, you can have a look to our job lifecycle. So when you land on the login nodes, you can access to the computational resources by submitting a batch script. Then your job goes in a queue. Then it is assigned a priority, and then you can run your job with different types of workloads that you have asked. In particular, in this slide, you can have a look to the different patterns in workload that you can find in our institute. So because of it is very heterogeneous, you can find different types of workloads. It depends on the task that you have to perform, on the workload about biomedical data that you have to process, or some other users, for example, use this type of workload in order to understand how many resources are needed, for example, to run a particular type of job. This slide is about the use of GPU. So as I said to you, in the old system, GPUs were not used. Now they are used, and we can find 2 different types of GPUs. You can ask, why do you prefer to use a particular type of GPU or another one? It depends on the task that you have to do. So for example, if you have to work with AI workloads, machine learning, deep learning, GPU-enabled scientific applications, the first one is better. While if you have to work with, for example, interactive jobs, remote desktop, visualization tool, you have to work with the visualization nodes. So it's better in this way because our HPC cluster is very scalable and very flexible about the task and the asks that the users need. Another issue of our cluster is about the storage architecture. So we deal every day with biomedical data that can be patient data, genomic data, other type of data that are very sensitive, so they need a particular type of governance, security, and privacy policies. Also, another issue is that based on the type of the task that you have to do and the data that you have to manage, you can adopt a different type of partitioning data. So we organize the data storage in this way. There is a local scratch that is in the node that can be used, for example, for fast temporary input-output jobs. Then we adopted with the use of the new cluster, the BGFS, that is a new parallel file system that can be used, for example, for high-performance parallel storage jobs. At first it was about 100 of terabytes, now it has been doubled, so it's 227 terabytes total. Then we have the legacy storage that can be divided into HPC NFS and HPC CCM that are used, for example, for long-term data storage and the legacy scratch. HPC NFS is for IEO, while HPC CCM is for Centro Cardiologico Monzino. Then also we adopt different strategies to prevent all the data to stay on our cluster, because we need to refresh daily the storage and also to maintain active the data. So we are daily or weekly performing some archiving pipelines in order to remove the old data and to send them on the Azure cloud. The last slide that I will present to you is about the data lifecycle. So here you can find some schemas and tables about other information on data. In particular, we also are adopting different strategies to prevent failure for data, and also to have different types of backups on our cluster. So mirroring or snapshots or a data recovery system were adopted in order to prevent this type of failures. As last thing that I want to share with you is that we are doing a daily communication with the users. There is a great communication about the use of the new cluster, especially to the people, for example, that is not common to use this type of resources, and in particular about the use of GPUs that in the old system were not used. So nowadays they are a bit under-allocated, so we need to make users aware of this type of GPUs, and they are improving that. We use, for example, these for structural biology, AI, and so on. And also about the use of data storage, because it's not possible to use a particular type of partition to, for example, maintain long data storage, term data storage, and so on. So they are very happy about this new system. The feedbacks are good, and they are making aware about that. So they are improving daily their way to work. Now, thank you for your attention. I will pass my words to Ali, that will continue the presentation.
Thank you. Okay, Chiara showed us how we made easier access to the HPC resources. I want to focus on the point that how in the background the things has happened. Starting with the reproducibility. Reproducibility is one of the main concepts that is important in the scientific computing. We made separate the software installation from software usage, which Lmod provides us the access to the load, switch, and remove the modules. And EasyBuild will provide us the easy access to install the application and building the softwares. Together, they allow us to maintain the consistent environment and also for the user to have access to the different versions of applications and without changing their workflows. Open on demand plays a central role in our user-centric HPC. Our researchers, they can access to the user interface through the browser. which can be so much easier compared to the traditional command line to access to HPC that it can be intimidating for the wet lab researchers and junior scientists. And this access is not replacing the HPC concept, but it just exposes a familiar interface through the web browser. And the important thing is the jobs, they are not running locally, but they are executed by the normal resources and managed by SLURM. And for many users, it was the first time that they were using these resources and allocations using open-on-demand web browser. In addition to the basic features of open-on-demand, which are file manager, active jobs, job composer, and shell access, there are more interactive apps, which are desktop, code server that they can have development directly on the cluster, Jupyter notebooks for exploratory analysis, and the RStudio for bioinformatics and statistical work. And containerized environment, they can help us to keep consistent environment for reproducibility and easier access to the tools. A typical workflow that they can access through open-on-demand is the locating and or uploading the data, develop and test on the pipelines using some Jupyter, RStudio, and the code server. And when they are validated, they can move to the big data set and executing by the SLURM. And this process, they can be monitored either by open-on-demand or by the standard SLURM via a command line interface. The governance is as much as important as the performance. Making easier access to the HPC does not mean to reduce the security or control. For this reason, we made our institutional identity manager to Active Directory, and external access is done by the VPN and a multi-factor authentication. Authorization is managed by group, POSIX permission, access control leaks, and allowing to have different access for the technology units, groups, and project teams. Access and project membership changes, they can be done through a formal approval to our institutional help desk, which can be reviewed before getting granted. And this is particularly important when we are working with the patient's data. And in the end, the data, they can be moved and authorized only to the project groups and the Linux specific permissions. A successful HPC platform has a visibility for both administrations and the users. For the user perspective, open-on-demand provides job status, user resource usage, logs, and also visibility in the command line interface using SLURM tools like SQ, SAccount, SF, and SStat to understand how the performance of the job are done. From the operator perspective, these monitoring dashboards like Grafana, alerts, and health check, they can have visibility into the performance and the status of the cluster. Users, they can request for the support through our help desk system, and advanced issues, they can be done by the dedicated support channel like the Jira of the HPC Now. Monitoring can create a feedback loop that helps the user to optimize and make easier efficiency of the future analysis. This is our daily basis monitoring using Grafana, which in the left we have the SLURM efficiency dashboard that helps us the dedicated resource usage, which it shows us CPU underused, wasted resources, efficiency per user, and this helps us to cure and tune the jobs request. On the right, we have monitor of the health of the infrastructure, which shows us CPU usage, memory, and storage activity, together with the node status. Some few principles that we learn through this transition to balance usability, governance, and the performance are the followings. SLURM remains our source of truth for the resource allocations, accounting, and management. The web-based interaction through Open On Demand made easier access for most of our scientists, which weren't command line users, and it didn't hide the underlying HPC concept. The other principle is match the storage to the workload requirements. Different storage types for scratch and cold data archiving are necessary for performance and the fourth is the investing in reproducibility. Tools like EasyBuild and Lmod creates a software environment that is consistent over time. And finally, treat the permission and governance as a part of the workload, not afterthought. So, at the outcome of our transformation, as Chiara mentioned, we have now supporting 200 users that they are clinicians or researchers, and more than 15 new users joined. And in the end, we have 90% of our community access through Open On Demand, which before they were so much less because they didn't have command line expertise. And the important thing is that this increase in adaptation was achieved without removing the principle of HPC. While we moved from PBS to SLURM, the account scheduling, governance, and accountability remains central to our platform. With making easier and lowering the barrier to providing access to HPC, made it easier for most of our community to access our resources. Before closing, I would like to acknowledge some of our partners and collaborators which help us with this transformation. Building a user-centric HPC platform is not only a technological challenge, but also an organizational one. This project brought together expertise from different areas like storage, automation, management, and security. Technology reply contributed to our platform operations like cloud storage, data engineering, and data lifecycle. Lutech supported our user administration, permission, and identity management. Do It Now group provided the expertise in HPC operations, storage, monitoring, and platform support. Lenovo delivered the HPC infrastructures like compute, GPU, storage, and networking resources. Thank you for your attention. We are ready for the questions, and if you have any further, you can have this contact of us. Thank you.
Thank you very much. Any question from the audience?
Hello, I have a question related to reproducibility. Is that if you have evaluated the option to use NICs or NICs packages to support like installing software on your cluster?
Sorry, can you repeat, please?
Yeah, have you evaluated the idea to support NICs or NICs packages to install software in a reproducible way, or just Lmod?
No, mostly we're working with the Lmod and EasyBuild because in our side, we are not so many expertise in HPC, and it's easier to configure and install, and also for the user to use them as the daily basis.
Okay, thank you.
Any other question? Okay, so I have a couple. So first of all, 19% of the users using Open On Demand. That's a very good thing. And I'm very happy to hear that. Also because I contributed. So I was wondering about your different kind of workloads. You already show us the different kind of jobs and the workload that are used. how are you handling the different priorities that these generates? Because you are a research center, but also a hospital, so I imagine that you have some workload that are high priority, because you need to have the result from a patient that needs some treatment, or on the other side, the research one that, I know that our users, they want to be first and hurry, and my job needs to run now, but have less priority on the cluster. How are you handling this?
We created a specific queue, which Chiara mentioned is bioinfo genomics. And our pipelines that they have the most priority, they are working on that. It has a dedicated resources and is reserved. So except of this, we have also another kind of a reservation that in advance, if we know some pipelines, they need to access to the resources, we set this reservation for 2 weeks, for next 10 days, for tomorrow, that in this time, either no one can access, or those resources, they are reserved for the users to do their analysis.
We have time for one more question? Okay. Thank you very much for your presentation.